Good afternoon. My name is Carson Roberts from Headwall Photonics, and today I'd like to talk about bidirectional reflectance distribution function striping and stray LiDAR points. These are a couple of artifacts seen in some customer data that I have analyzed and basically can blame them both on our friend the sun, which gives us light, but unfortunately doesn't give us perfectly uniform light all the time. So the original problem came from our friends, a customer at Technical University in Munich. They'd taken a flight over a wheat field, and as you can see in both of these images, there's some interesting striping, some apparent intensity variation in overlap regions between flight lines. Now, this is a sort of a funny false color image. It's a monochromatic image where it has been colored by intensity, with with green being dark and yellow being bright. And on the left, you can see the mosaic made in the Headwall spectral view program, where in the overlap regions, you see a bunch of horizontal stripes. And on the right, you can see the same data, but mosaiced in QGIS, where subsequent images are just placed on top of each other. And you can see much more clearly this variation in intensity as we travel from west to east across the image. And the question is this something wrong with the sensor, or is there something real going on in the data? And so I'm going to try and go through how I figured this out and what conclusions I can draw from it. So there's some overlap regions are dark, some overlap regions are not. And how can we do this? The first step is to be able to visually identify whether I was flying north-south or south-north. And so I do this by taking a look at how the sensor works. And this is something that's true pretty much for all of our systems. If you think about a quadcopter, it's going to be true for an octocopter or a hex as well. If all the rotors are giving the same thrust, the aircraft will sit completely still and a sensor mounted to it will look straight down. Now, that's not useful for our taking data with our sensors because we need some motion. In order to get motion, you need to put more thrust on the rear rotors. That tilts the drone forward. It flies forward, but that means that it's going to be facing back along the way it had come. So I can then look and say, if I'm heading south, my field of view is shifted to the north. If I'm heading north, my field of view is shifted to the south. And so then I can go and look at the image and say this first one was clearly going south. Then the drone flew north, then south, then north, then south, then north, then south. So just by looking at these offsets at the end of the flight lines, I can unambiguously determine whether a flight was north-south or south-north in this example. There's some other examples where we're flying east-west, and we can apply the same logic to differentiating the flight lines there. So does this have to do with the sensor? Well, we do know that the sensor has 1020 pixels, and a possibility is the right side of the sensor is more sensitive than the left for some reason. So let's look at what happens when we're flying this sensor and we go back and forth, because it turns out there's different overlap regions for different sides of the sensor. So if I first fly north, then south, the overlap is going to be on the right side of the image. Remember, that was pixel 1019. If I have a southward flight line followed by a northward flight line, then the overlap is going to be on the pixel 0 side. And so if all these issues were due directly to non-uniformity, maybe it would be enhanced in one region and suppressed in another. And then similarly, if I'm flying east-west, again, my overlap region is either right side, or left side, left side. So if we apply that to the data, it really looks like the dark regions we see are when the left side is overlapped by the left side, and that's what I've colored blue in here. And so each of these blue overlap regions, except for the first one here, where there wasn't a complete flight line before it, that's where we see these darker regions. And so this could be due to the sensor, but as I will show you, I believe unambiguously later, this is not due to the sensor. It actually has to do with the sun and how plants interact with the sun. So originally, the folks at TUM sent me this Wilsheim flight, which had this pronounced striping. I made some preliminary conclusions that it might well be due to this bidirectional reflectance distribution function, which I'll talk a little bit more about in a minute, and asked them if they had any other data, and they sent me 3 other data sets. One at Farnshausen, which is mostly north-south, one at Sieblerfeld, which is somewhat east-west, it's closer to 45 degrees, and one at Weizhoff, which is pretty much east-west. And I came up with an analysis and applied this to all of these and try to show at the end how I can explain all of the intensity variations we've seen by this combination of solar angle and how plants tilt their leaves. So let's go first on to this Wilsheim, the first data set, and let's look at 3 flight lines. And I'll explain a little bit later, but as you can see, all the cubes in a single flight line are going to have the same last 3 numbers. So this northward flight, I call the 884 flight because they all end at 884, an 030 flight and an 096 flight. And in the next couple slides, I'm going to be looking at one of the cubes from each of these. But first, let's take a look at the actual orthorectified stripes. And so this is the 030 stripe. What I've done is I've cropped off the edges and then applied some brightness and contrast, and it really looks like on this flight, the left-hand side, which is the west, is dimmer than the right-hand side. And indeed, I can take this image right here, I can load it up in an image processing program, get its average horizontal profile, and it very clearly increases from left to right. That's from west to east. And of course, there are some artifacts due to tractor lines in the flight. Those are something that we will hope to ignore going forward. So rather than trying to crop the whole image after being orthorectified, let's just look at the raw data cube. So if we go back, you can see that in the orthorectified data cube, you have wavy edges with straight lines in the middle. And in the raw data cube, we have wavy lines in the middle and straight edges. And so here's a northbound one, a southbound one, and another northbound one. And when I enhance the brightness and contrast, both of the northbound flights are dark on the left-hand side, and the southbound flight is dark on the right-hand side. And then we're going to associate those with whether it's east or west. The answer ends up being the dark sides are always in the west. So rather than just looking at those, I can then take each of these cubes and take a horizontal profile of it. And we see again, this 884, it's going up from west to east. The 030, it's going down from left to right. And then in the last one, it's going up again. So this is consistent. But I want to have something where I can take larger averages because all these data are pretty noisy and in some sense look like they're dominated by these bright stripes from the tractor lines. So what I want to do is, first off, as I just said, I'm going to figure out what the flight lines are by the cube numbers, and then create these monochromatic images at 669 nanometers. That's in the red. That's one of our standard RGBs, values that we use in the spectral view. Examine all these, and this part here is subjective, and try and find uniform scenes. I'll talk about what that means, and then calculate the horizontal profile of each of the uniform images, generate an average profile for each flight line, and then group the flight lines according to flight direction and generate average profiles for those. How do I know this? Well, because each of the flight lines, each of the cubes is 1,000 lines, the last 3 numbers will be the same for all cubes in one flight line. And so that's how I can generate a list and say, just by the name of the cubes, I can see which one is which. So here's an example from one of the other flights. I'm showing at the top here an orthomosaic, an RGB from the orthomosaic. It was flown in this sense from left to right. And we look at the first data cube and I say, that's non-uniform because I see this very bright road here, and that's definitely going to impact whether I see a gradation from right to left. So I don't include that one. The next one, that's mostly uniform. The next one, mostly uniform. The next one, mostly uniform. And so for each of the flight lines, for each of the flights, I went through and manually eliminated those images that had non-uniformity, significant non-uniformity in them that might mess up the analysis. And so then what I can do is automatically go through and generate profiles for each of these selected cubes. And if I look at 3 of these, there's not a strong trend. It looks like it goes down to the right. Not so much in this 3rd one, though. It's pretty flat, but there were 18 flight lines. And when I take the average of all 18 flight lines, there's a very clear trend of light on the left and dark on the right. And so this is the analysis that I applied to all the flight lines. And so for this Wilsheim, we can see all the north-south profiles. Now, when it's flying north-south, that's down here, then east is going to be to the left, west is to the right, and the west-hand side is dark. For the south-north flight lines, where east is to the right, the west is to the left, and the west side is dark. And so this is consistent through all the flight lines. And then, again, a bit of variation. And so these all represent north-south flight lines. These all represent south-north flight lines. And so let's average those. And then we see quite a trend here where the south-north profiles, they are dimmer in the west and brighter in the east. And the north-south profiles are also dimmer in the west and brighter in the east, but they are overall brighter. And this is the first place I'm going to try and talk about this BRDF. If we remember that the drone is facing back in the direction it came, if it is flying from south to north, it is looking to the south. It's the northern hemisphere. So the leaves are pointed towards the sun. And so the leaves are pointed towards the sun. When I'm looking to the south, I'm looking at the bottoms of the leaves. And that's why we should see a systematic variation where northbound flight lines are going to be dimmer than southbound flight lines because the northbound flight lines are looking at the undersides of the leaves and the southbound flight lines are looking at the tops of the leaves. And I have some graphic representations of that in a later slide. So can I then explain this intensity striping? So what we typically do is we program our flights so that we travel north-south, south-north, north-south, south-north, and we program an overlap of about 30% between the flight lines. So what I've done is I've taken this average south-north flight line, this average north-south flight line, and displaced them by 30% of the sensor field of view. And what becomes clear is these red overlap regions, the difference between the two is small. And in the blue overlap regions, there's a very significant difference in intensity between the north-south profiles, which are bright, and the south-north profiles, which are dim. And these blue areas correspond to these blue areas, which we had already said were the dark areas. And so at this point, it seems quite clear that the majority of this variation is associated with the fact that the different flight lines have different profiles. Why do they have these different profiles is the next question that I want to try and answer. And so it's possible that it had to do with the sun angle. That's what I believe. It's also possible that it's due to polarization, but I have a good enough explanation that it's due to the sun angle, so I suspect that's probably not. But the bottom line is there's always, in this north-south flight, it's always darker on the west side than the east side. So what's going on? On the left here, I have the sun at nadir, and I'm approximating the leaves by a bunch of squares. The leaves are all facing straight up, so they look square. If we look at it from the side, they're squares with a little bit of perspective. If the sun is in the west, the leaves are going to face towards the west. They'll have a lower aspect ratio looking vertically, and they'll be illuminated on the side that's facing towards the sun. If the sun is in the east, the situation is opposite. So let's look at that example of the sun is in the west. Here's the west, here's the east. The sun is here, the leaves are tilted towards the sun, and so these top surfaces of the leaves are all illuminated. On the east side, the imager is looking at the tops of the leaves. Those are going to be bright. On the west side, the imager is looking towards the bottom of the leaves, and those are going to be dark. And we should see similar variations in the north-south direction for east-west flights. So, does this make sense? If I look at a solar angle calculator for this first flight, indeed, the sun was in the west. It was in the afternoon, around 2 o'clock in the afternoon. And so the leaves would have been pointed towards the west. And we should expect, as by that basic earlier analysis, we should expect darker in the west. let's do the same thing for the other flights and make some predictions. So for this Fahrenhausen's flight, the sun was in the south and the east. And it's also north-south, so I'd expect on this one for the east sides to be dimmer. For this flight in Sieblerfeld, again, the sun was even further in the east, and the south-north stripe should be dimmer, and all flights dimmer on the east side. As we'll talk about later, this flight was taken early in the year, and the crop was very young, and so the reflectance was really dominated by the ground. So we didn't really see much in this one. And then here's another one approximately east-west, and this one again, the sun was in the east. So let's look at that. So that last one, this east-west, the sun was in the east, and it sure looks like the south on both sides is dimmer. Okay, and that's what we said, because the sun is in the south, the leaves are going to be pointing towards the north. They're also going to be pointing towards the east. And so we would expect that south side to be dimmer. When we bring them together, we see, interestingly, on the average, there is no real east-west or west-east variation. It seems as though this data set is really dominated by the tilt of the leaves towards the south. For this north-south one, and as we call a little less of a solar angle, we do see some striping. And what we see here is for the south-north profile, they both seem to be a little bit darker, but again, this north-south is brighter. And so that's probably what's going to dominate the striping there. For this last one, not much coverage. There's no real clear trends, and maybe a little bit slightly darker going towards the south. And so my conclusion is it's very likely that this variation that we're seeing in intensity is due to what a colleague of mine called dynamic bidirectional reflectance distribution function, the dynamic part being the leaves actually tilting towards the sun. What was surprising to me was the strongest effect, the initial customer problem, was in a wheat field. And I don't typically think of grasses as having leaves that tilt, but I would say from this, they very clearly do. So there's this, all the leaves are going to be tilted toward the south. In the morning, they're going to be tilted towards the east, and the south, in the evening, they're going to be tilted towards the west. And these together explain most of the variations that we've seen. Unfortunately, it's not clear to me at this point, and I'm unable to present you with, here's the way to fix it. But certainly, flights near solar noon will minimize the east-west variations in these data. And just be aware that if you see this in your data, it's not the sensor, it's what's actually coming up from the ground. So now I'd like to shift gears and talk about another artifact that I looked at a couple years ago, which turns out to be kind of due to the same thing, the solar angle. And that is, when we fly the LiDAR, we occasionally find many, many points high in the sky, near the ground, and below the ground that are clearly not reflections off the drone, nor actual points on the ground. And so what are they? And so one of the interesting things is when we started working on this, we only see these on sunny days. On overcast days, we will get extra points, but they're rather randomly distributed. And since they happen on sunny days, the hypothesis is maybe the LiDAR. So what the LiDAR does is it shoots out a 903 nanometer laser beam and then looks for a reflection of 903 nanometer light some few nanoseconds after that first pulse. If the laser fires when the sensor is pointed towards the sun, it will get 903 nanometer light that didn't come from the laser, came from the sun. And so let's see if we can find some basis for that argument. So I've broken up this point cloud. There's the trajectory and the ground points. And so depending upon the drone, we get quite a few reflections either from the drone body or from the rotors, and we can actually see an object in the point cloud that is the trajectory. And so if we look just at the trajectory and the points above the trajectory, these are what I'm calling sun-directed points, and I have an explanation for them. There's another set of points above the ground which seem to be correlated with the flight lines, but I don't have a good explanation for them. I believe they're due to internal reflections inside the LiDAR. And then there are points below the ground as well. And what I see is there is the ground level. We flew this at about 55 meters above the ground. There's another layer that's 20 meters below that, another layer that's 20 meters below that, and another layer that's 20 meters below that. Really consistent. I don't have any idea why. But again, we only see these when we have bright sunlight. So I did some collaborations with my friends at Rochester Institute of Technology, and they shared a data set where they flew west, east, and north, south, and they had lots and lots of points up in the sky. And I found that it looked like they were mostly, the points were mostly pointing towards the south and east. And so I found the best results been looking at the east-west trajectories, because in each east-west flight line, it makes a turn where it's flying approximately north-south. And in each of those turns, it's flying straight for a short amount of time, and we see a burst of points. And so those, what I'm going to analyze to say, are those pointing towards the sun? So I get a solar angle calculated for the time that that was flown in Rochester, and the sun was an azimuth of 100 degrees. When I take an orthorectified image, so that is north, south, east, west, of the point cloud, and I look at one of these burst of points, they are going at 100 degrees. And so that to me says very clearly that these bursts and then the sheets in the other direction are due to the sun coming in, and that's why we don't see them on cloudy days. So I don't understand part of this. I've presented this before, and I'm hoping that someday some graduate student is going to think this is a cool thing and figure it out. But basically, if you see lots of extra points in your point cloud, it's not a defect of the sensor. It's actually coming from the sun. So that's my basic story. I would really like to acknowledge my collaborators, the folks from TUM, Lucas and Ludwig. They were very gracious to share data with me, and have been very, very patient in waiting for their answer, which I haven't given them until I finished this talk. This started with a customer support ticket. We do answer all of our support tickets. Most of the time, we can give you a simple answer. If we don't, it starts a research project like this. And so I look forward to more customer complaints, customer problems, and to hope customers solve them. And similarly with the LiDAR data, our collaborators and customers at the University of Rochester Institute of Technology, Tim and Nina, shared their data with me. So that's all I have for today. And in a minute, I'll be happy to answer any questions you might have.